The topic of this lesson is summing amplifiers. Let's first discuss the unity gain summing amplifier. A two-input summing amplifier is illustrated in the figure now shown. A summing amplifier has two or more inputs, and its output voltage is proportional to the negative of the algebraic sum of the input voltages. Let us assume we have two voltages, Vi1 and Vi2, at the inputs. The currents produced by these inputs are I1 and I2. The inverting input of the op-amp is 0 volts, and there is no current. This indicates that both input currents join at the summing point and form the total current I, which passes through R sub F. Since the output voltage is equal to minus the total current times the feedback resistance, R sub F, it is then also equal to minus the quantity I1 plus I2 times the feedback resistance. In terms of the voltage drops across R1 and R2, the output voltage is equal to minus the quantity Vi1 divided by R1 plus Vi2 divided by R2 times the feedback resistance. If all three resistors are equal, that is R1 equals R2, which equals R sub F, then the output voltage is equal to minus the quantity Vi1 plus Vi2. Thus, the output voltage is the sum of the two input voltages. For n inputs, where all resistors are of equal value, the output voltage is equal to the sum of all the input voltages. As an example, determine the output voltage in the figure now shown. Since the output voltage is equal to the sum of all the input voltages, the output voltage is equal to minus the sum of 3 plus 4 plus 2, or minus 9 volts. Let's now discuss the summing amplifier with a gain greater than unity. When the feedback resistance R sub F is greater than the other resistors, which are all equal, the amplifier has a gain of R sub F divided by R, where R is the value of one of the input resistors. Therefore, the output voltage is equal to minus the feedback resistance divided by the resistance of one of the equal input resistors times the sum of all the input voltages. For example, determine the output voltage in the summing amplifier now shown if R sub F equals 6 k ohms and R1 and R2 equals 2 k ohms. Since the output voltage is equal to minus the feedback resistance divided by the resistance of one of the equal input resistors times the sum of all the input voltages, the output voltage in this example is equal to minus 2.7 volts. Let's now discuss the averaging amplifier. A summing amplifier can be designed to produce a mathematical average of the input voltages. Here, the ratio R sub F to R is made to equal the reciprocal of the number of inputs. For example, show that the amplifier in the figure shown produces an output which has a value equal to the mathematical average of the inputs. Since all the input resistors are equal, R is equal to 40 kiloohms, and the output voltage is equal to minus the feedback resistance divided by the resistance of one of the equal input resistors times the sum of all the input voltages. The output voltage in this example is equal to minus 3.5 volts. Calculating the average of the input strictly from a mathematical perspective results in 3.5 volts also, as indicated in the equation now shown. The next type of summing amplifier is the scaling adder. If each input resistance has a different value, a weighted value can be obtained for the output voltage as determined by the equation now shown. For example, find the output voltage. The weight of input 1 is determined by dividing the feedback resistance by the value of R1, or 50 kiloohms, divided by 85 kiloohms equals 0.588. The weight of input 2 and 3 are determined in the same manner as shown. The output voltage is then determined by multiplying each weighting factor by each corresponding input voltage, which results in an output voltage of minus 6.774 volts.